Hello everyone, in this video we'll be looking at section 13.1, which is Introduction to Functions of Several Variables. Subsection 1, Functions of Several Variables. So far we have dealt only with functions of a single independent variable, like y equals x or f of x equals x, y equals f of x. But in any case, we've only dealt with one variable. Many familiar qualities, however, are functions of two or more variables. Three such examples. One, the work done by a force is equal to the force times the distance. So work is a function of both the variable force and the variable distance. The volume of a right circular cylinder is pi r squared h. So that's a function of two variables, the first being the radius r and the second being the height h. And the volume of a solid is length times width times height. So that's a function of three variables because I have a length, a width, and a height. If a function is a function of two variables, we use the notation z equals to f of xy. So remember, before when we were dealing with one variable, it was y equals f of x, right? Because x was our independent variable and y was our dependent variable. Now what's happening is z is going to be our dependent variable and x and y are both independent variables. So I plug in an x and y and I get a z value. Or in the case of three variables, I plug in an x, y, and z as my three independent variables, and w is then my dependent variable. All right, so it's just extending everything we already know to more variables. Okay, so definition of a function of two variables. Let D be a set of ordered pairs of real numbers if to each ordered pair x, y there corresponds a unique real number f of xy, then f is a function of x and y. So again, the idea here is I have a pair of independent variables x and y. I plug them into this function and I get f of xy, right? And that is my output or my dependent variable. Again, we typically denote it by z. The set D, the allowable x and y values that I can put in there is the domain, just as in the case of one variable x, whatever values I'm plugging in was just the x value, or the one independent variable, that was my domain. Here our domain is going to be two-dimensional or three-dimensional, depending on how many variables we have. And the corresponding set of values for f of xy is the range. Right? So what we plug in is the domain, what we get out is the range, just as before. For a function z equals f of xy, x and y are called the independent variables and z is the dependent variable. The domain of a function f of xy is a set of all points xy for which the function is defined. So that's the exact same as in the case where I was looking at y equals f of x, right? The domain was the allowable x values, right? And so that ended up being like a real line, right? I would have negative infinity maybe to 0, union 0 to infinity or something like that, and that was a domain, and that corresponded to a real line because it was one variable, so it was a one-dimensional space. Now my domain is two-dimensional, right? It's an x and a y. So when I think about this, I'm plugging in both x and y values. So my domain will correspond to an x and y shape in space, right? Or a plane in space, that's a better way to put it. Some sort of plane in space. Okay, so first question, find the domain of the function f of xy equals to the square root of x squared x squared plus y squared minus 9 over top of x. So just as before, when we were looking at the domain of functions of one variable, we need to see like where bad things happen. So the first bad thing that can happen is I can't have x being equal to 0, right? Because if x is equal to 0, then I'm in trouble, right? So first, x cannot equal to 0. Well, think about the coordinate plane, right? Because now we have points x and y that we are allowing in our domain, right? So what does x being equal to 0 correspond to? Well, if I think about the plane, if I have a value that's on the y-axis right here, then everybody on the y-axis has x equal to 0. Right? So in other words, because I can't have x equal to 0, that means that I can't have any point on the y-axis. right? So here we cannot be on the y-axis. Okay, now the other thing that can happen here is if you look, we have a square root, right? I have the square root of x squared plus y squared minus 9. So if that's a square root, what do we need to have happen? We need to have x squared plus y squared minus 9 greater than or equal to 0, right? Because that means that that means that there'll be no negatives in my underneath the square root. So in this case, I end up getting x squared plus y squared is greater than or equal to 9. Well, what does that remind you of? That should remind you of a circle of radius 3 centered at the origin, right? And so recall that x squared plus y squared equal to 9 is a circle of radius 3 centered at origin, right? So in this case, what does it tell us? Because we have greater than or equal to 9, we know that our domain, if we need to satisfy this, right? So our domain, what we're allowing is all points on, why on, because of the equal to part, on a circle, on and then or outside, because we have greater than or equal to. So we've got to, whatever we've got has to be bigger than the circle, right? So all points on or outside a circle of radius 3, right? So if I'm going to write what my domain is, I'm going to write it out in words, and then I'm going to write it out as it should look like in set builder notation. So my domain here is going to be all points, because again, my domain is not just x values or not just y values, it's x and y values. So all points x, y on or outside a circle of radius 3, except those values or except those points on the y-axis, right? Because we can't be on the y-axis due to our first idea that we have x in the denominator, right? So if we're going to put that in set builder notation, that would be, okay, all x, y such that x squared plus y squared is greater than or equal to 9, right? That's the first piece. And such that x does not equal to 0. Right? So that's our set builder notation for what the domain should be. And now remember, the domain is it's a plane, right? And so it's on the x and y coordinate plane. So let's go ahead and just draw what that would be. Right? So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay. And so if I were going to draw what the domain would be, I know I can't be on the x-axis, the y-axis, and I know that I have all these points on the surface of a circle here of radius 3. I know that I can't be inside of that circle, so I'm not going to fill it inside, and I also know that I can't be on the x-axis or on the y-axis, so that's why I'm going to put like dotted lines there. And then now if I'm going to color in my domain, it would just be everybody on the outside of this, right? So all this, but not the y-axis and not inside that circle. Right? So what I'm coloring in here is the domain. Every single point except inside the circle and except on the y-axis. Right? So that is the domain illustrated. Okay, so as long as my x and y values lie outside of there, say like this point right here, that would be a point x, y that I could plug into my function to get z, my f of x, y value. Okay, so let's look at another one here. Find the domain. This time it's three-dimensional. So we have x, y, and z. So since it's three-dimensional, that means that now it's not a plane that's going to be our domain, but it's going to be some sort of like three-dimensional object. Okay, so this x in the numerator doesn't hurt us at all, right? X can be negative or positive there. However, what we've got going on in the denominator is troublesome, right? So I need 9 minus x squared minus y squared minus z squared. I need it to be greater than or equal to 0 because I need to have only non-negatives going in the square root. But it actually also can't even be 0 because if it's 0, then I would have a 0 in the denominator. Right? So I need this to be a strict inequality. So now I get 9 is greater than or equal to x squared plus y squared plus z squared. Right? And what do we recall? Remember that x squared plus y squared plus z squared equals to 9 is a sphere of radius 3 centered at the origin, right? So now when we go to state our domain, remember we want our guys that we plug in to be smaller than that and not equal to. So if I were going to write out the domain, it would be all points, this time x, y, and z, right? All points in the 3 space that lie strictly inside, so not on the edge or on the shell, of a sphere of radius 3 centered at the origin. And if I were going to write this out, this would be x, all points x, y, and z, such that x squared plus y squared plus z squared is strictly less than 9. All right, so it would just look like, if I were going to draw this out, it would just be like a ball in space, but somehow not have the shell or the edge colored in. All right, you can see that's kind of hard to draw, so that's why we're just thinking about it out loud. Okay, so a function that can be written as the sum of different functions of the form some constant times x to some power times y to some power, where c is just some real number and m and n are non-negative, is called a polynomial function, right? So in other words, anytime I just have powers of my variables, positive powers of my variables, right? I don't want negative because that means throw it in the denominator, and I don't want fractions because that means take roots of it. But anytime I just have non-negative integers, right, non-negative whole numbers for my powers of x and y, and I multiply them together and add them up, that's what's called a polynomial, much like what a polynomial is called in one variable. So some examples look like f of xy is x squared plus y squared minus 2xy plus x plus 2. Right, that would be one example. Another example would be 3xy squared plus x minus 2. And so we can do composition of functions, just like we can do compositions of functions in one variable. We can do sum and difference of functions. We can multiply functions. We can divide functions. All the stuff we can do with polynomials of one variable, we can also do with polynomials of more variables. A rational function is the quotient of two polynomial functions, right? So much like when we looked at rational functions of one variable, maybe like x squared plus 1 over x minus 2, right? That was a rational function of one variable because it had a polynomial on the top and polynomial in the denominator. Same thing goes for polynomials of more than one variable, right? So for example, if I had this x squared plus y squared minus 2xy plus x plus 2, right? That first polynomial over 3xy squared plus x minus 2. This would be an example of a rational function in two variables because it has a polynomial in the top and the polynomial in the bottom, right? So everything we know before is just being extended to functions of more than one variable. Okay, so let's go ahead and end this video here, and we'll pick up in the next video with example, with subsection 2 here, the graph of functions of two.